quantum mechanics, black holes, genetic regulatory networks, systems biology, ecosystem science, artificial intelligence, and machine learning. Science, math, logic, probing the mysteries of time and space. Get your nerdy talk here with everyone's favorite scientist on Talk Nerdy to Me.
Hey everyone, this is Dr. Jack. Join us as we travel through space on this little blue ball during our temporary visit to the third planet around a particularly nondescript yellow star, and as we contemplate the world, the universe, and everything around and within us. Our goals are comprehension and understanding. Our tools are science and observation. Our vehicle, our minds, and our imaginations. We will be piecing together myriad facts, figures, conjectures, and speculations on the really big questions like, what existed before the universe? What is the fundamental nature of time? What is gravity? What is consciousness? And what is life? We'll approach these questions with a childlike curiosity, a hunger to learn and hopefully discover something about the universe and about ourselves. And we will hopefully also end up with more questions than answers, because, after all, science is for asking questions. So, let's begin. Good morning, everyone. This is episode 3 of Talk Nerdy to Me. Today's date is November 2nd, 2020. I have 2 resources to share with you today. First, let's set it up. Einstein's theory of special relativity became Einstein's theory of general relativity, and it could remarkably explain some of the anomalies that were observed that Newtonian physics could not explain. Some of those anomalies include some of the details of, say, Mercury's orbit around the sun. But Einstein's theory did much more than explain some of the strange features of the universe. It also made very specific predictions about gravity. It made very specific predictions like gravity should be able to bend light. As an empirical researcher, these tests of the predictions enhance confidence in Einstein's theory of general relativity until we get to the quantum scale. Quantum mechanics is a school of thought in fundamental physics that has a number of very strange features. First of all, unlike Einstein, Einstein's theory came about through thought experiment. So it was theory first and then data. Quantum mechanics came about through observations of mathematics, certainly some of those strange things that came through the Dirac equation, for instance. However, the reason why we still hear about quantum mechanics and this irreconcilable relationship between general relativity and quantum mechanics is because it too has its own body of empirical observations that are only reconcilable to the large extent with general relativity because general relativity never saw it coming. General relativity did not anticipate some of the strange behavior of the universe at very small scales. It did anticipate some very strange experiences of observers at very large scales. And notice that in our mind, sometimes we interchangeably use features such as words such as features of the universe and experiences of observers. And this is another difference between quantum mechanics and general relativity. General relativity makes some pretty strange, counterintuitive predictions that do involve the observer, the juxtaposition of one observer to another, or the juxtaposition of one observer to another and to a moving object or moving observers. And those strange things include outcomes such as when someone who's traveling very fast towards a particular distant galaxy may actually be in time in a different place relative to the galaxy that they're traveling from, relative to another traveler who's traveling in space and in time away from that galaxy at a very fast rate. And when the two pass each other in space, the events that are happening in the galaxy that observer one is anticipating may have already happened for observer two. This strange relativistic view is unsettling. It also is reconciled mostly due to the beauty and the elegance of the mathematics of general relativity, but certainly confirmed. There are things like time dilation absolutely have been confirmed empirically. And so if we didn't adjust our understanding of where satellites were, for instance, in the sky, because they travel so fast, and they travel fast for so long, our understanding of where they would be off by a non-significant amount. Time dilation being one thing, involving the movement of matter through space and time, leading to time dilation, requires reconciliation with our intuition. Similarly, quantum mechanics requires reconciliation of odd things such as superpositioning, in which an object, subatomic particle, say, can seemingly be at two places at the same time. This idea that an object has a probability of existence is different than the statistical probability of a feature of an individual in a population. That a single object may have a probability distribution of existing leads me to the concept of a continuum of matter, which we'll visit in future episodes. However, today we're going to continue along the theme of looking at ways to explain some of the anomalies that we think that we see in the cosmos, specifically around the time of the Big Bang, to truly fundamentally understand the universe we find ourselves in, the universe of which we are a part. We have to try to understand how to hopefully explain some of the strange features that we see. I won't belabor much further any of the details about this. However, we're going to be talking about something called the Big Bounce. I'll let the articles speak for itself and then I'll do some reflection, but the Big Bounce is an alternative to the Big Bang. Let's call it a clarification to the Big Bang, in that the Big Bang itself only goes so far and fails to explain some of the variation that we see when we look out in the cosmos. The Big Bounce is embodied in a couple of different mathematical theories. One is called quantum loop theory, and we'll be reading an article about that today. Before we get to that, we're going to go to the Simons Foundation webpage, and they have a Bang, Bounce, or Something Else article. It was published April 22nd, 2020. That article begins, "Time began at the Big Bang, or did it? Alternative ideas, including a universe that repeatedly reboots itself, suggest something came before the Big Bang." Here we go. One thing that makes cosmology fun is how much you can notice from simple observations. Why, for example, is the night sky so uniform? If you look in opposite directions to the farthest reach of your vision, the universe looks pretty much the same. Yet those distant places have never communicated with each other. They are too far apart. Light from each side of the sky is now only reaching us in the middle, so it hasn't had time to cross to the other side, and no physical process links the two. So why do they look alike? The uniformity is a glimpse of a cosmic prehistory. For 13.8 billion years, the universe has been expanding, cooling, and evolving. Textbooks often say that the start of this expansion, the Big Bang, was the start of time. But if so, those widely separated regions could never have attained the same temperature and density and other basic features of the universe would likewise seem explicable. That's all related to your assumption that there was a beginning of time. So why don't you give up on that beginning of time idea, says Paul Steinhardt of Princeton University. That was a simple extrapolation of Einstein's equations, assuming no change, even when you get to energies and temperatures that you have never been probed before. Most cosmologists think that something must have set the stage for the expansion we observe, although they disagree on what. Steinhardt was a co-author on the standard account, Cosmic Inflation, but has since turned against it and now promotes a competing model in which the universe is the latest round in a perpetual cycle of creation and destruction. Other scientists, too, are exploring alternatives to standard inflationary theory and to Einstein's gravity theory to fill in the prehistory. Some alternatives try to prove a pre-inflationary phase, says Greg Gabadades of New York University, who is Associate Director for Physics in the Foundation's Mathematics and Physical Sciences Division. Others don't use the inflationary mechanism, but still have a phase which is before the Big Bang, before the conventional expanding phase. Cosmologists might finally be approaching some closure to the question. The Simons Observatory, a ground-based array of telescopes designed to make definitive measurements of the cosmic microwave background, is scheduled to see first light in 2020 and reach the requisite sensitivity in 5 years. Among other things, it will search for gravitational waves from the prehistorical cosmic period, which some models predict and others do not. Both cases will be interesting, discovery or non-discovery, Gabadades says. What makes the expansion of the universe tricky is to think about that the universe, is not the same as our universe. We see only part of the whole, limited by how far light has been able to travel since space began stretching, a distance known as the cosmological horizon. In the standard Big Bang picture, not only does space get bigger, but we see ever more of it. The rate of stretching is slower than the rate of light propagation through space, so we can receive light from more and more distance sources, explains Anna Aegis of the Max Planck Institute for Gravitational Physics. The idea for a cosmic prehistory say that one or both of these rates used to differ from what they are now. During cosmic inflation, for instance, space expanded at a quickening pace, while the cosmological horizon stayed fixed. An observer during this period would see ever less of space. It's the relative growth of space compared to the horizon that's the important thing, Steinhardt says. The horizon also limits the range over which physical processes can operate. At first, two nearby regions were able to exchange material and even themselves out. Then, space pulled them apart until they exited each other's horizon, at which point they fell out of touch. Sometime later, inflation ended, ushering in the present epoch. Distant regions are uniform because they used to be close together. Similarly, the universe appears to be geometrically flat because the broad curvature of space, if it had curvature, was lost to view. Steinhardt and Aegis argue that space need not have grown at all to achieve this effect. On the contrary, it could have shrunk. Cosmologists have toyed with contracting models before, supposing that the universe will reach some peak size, collapse under its own weight back to a pinprick, and bounce to begin a new cycle of expansion and contraction. But those models did not seek to account for cosmic uniformity and flatness. In Steinhardt and Aegis scenario, these attributes are the result of the contracting phase of the preceding cycle. Moreover, they argue that space need not collapse by all that much before bouncing. Instead, it is the cosmological horizon that shrinks to almost nothing. In this scenario, the horizon is defined as how far observers can see before the bounce occurs, the distance that light can propagate before the bounce gets less and less, he just says. As the horizon closes in on observers, galaxies vanish from sight, and a curtain falls on the broad curvature of space. Space is becoming more curved in the absolute sense, but your horizon is shrinking faster, Steinhardt says. You're seeing less and less of it, so as you approach the contraction, as far as you can see, that patch looks extremely uniform and flat. If you could experience this process, you would lose sight of other galaxies, then stars in our own galaxies, then the moon and Mars, then Mars, and then the moon, and then the other side of the room. Soon your own body would cease to operate as a coherent being, and individual particles would live in utter isolation, no longer interacting. The universe would have completely atomized. All of its structures would be frozen in place, emerging from hibernation, only when the horizon was able to grow again. A shrinking horizon is a feature of other alternatives to inflation as well. In so-called Galilean Genesis, space initially expanded slowly and had no trouble evening itself out. At the very beginning, the horizon had an infinite size, and as the universe evolved in the Genesis phase, the horizon gets smaller, Gabadatas says. Additionally, energy fields and nonlinear interactions among those fields seeded space with matter and revved up its expansion, thereby putting the bang in the Big Bang. Commentary in the last episode, we discussed the reheating theory of the Big Bang. All these models have much in common. They require physics beyond present theories, new forms of energy akin to dark energy, and perhaps modifications to Einsteinian gravity. They require an even earlier epoch, the prehistory, to make the universe uniform and set up the conditions for expansion or contraction. They naturally produce not just one universe, but potentially infinitely many, either in the form of a vast effervescence of bubbles, as in inflation, or an endlessly repeating cycle, as in Steinhardt and Aegis' model. But the models have crucial differences too. Inflation occurs when the universe is hot and involves high energy processes, so it is prone to fluctuations that cause it to produce a high diversity of universes that vary in the distribution of matter and even some aspects of the laws of physics. Thus, space on its vastest scales is highly non-uniform, which is ironic because cosmologists came up with inflation in large part to explain the uniformity of our observed universe. Our universe is, if anything, a rarity, so the theory fails to make firm predictions for what we should see. Proponents of inflation have sought to tinker with the mechanism or supplement the theory with other principles to give it more explanatory power. In contrast, Steinhardt and Aegis' cyclic model avoids this problem because its processes occur at comparatively low energy. It produces universes that are broadly similar, with only minor variations from our own. As with many controversies, both sides make a good case, and the task of deciding between them falls to observers. Inflation would have had conspicuous gravitational side effects because it's a highly energetic process. When you produce density fluctuations at high energy, they also produce fluctuations in space-time itself, Steinhardt says. So far, searches for gravitational waves from this era have come up empty. If the Simons Observatory doesn't find any either, inflation is in trouble. Are the null results to date already uncomfortable? Yep, they are, Gabbidatas says. Already, they kind of are. Conversely, if the observer does detect primordial gravitational waves, Steinhardt and Aegis' cyclic cosmology is dead. If we see that, it will disprove many of the competing models, says Simons Observatory Director Brian Keating of the University of California, San Diego. A distribution of background radiation measurements offers another empirical handle on the problem. Currently, a histogram of temperature reading at different locations on the sky traces out a bell curve, a Gaussian. Any deviation from that generic shape would reveal what physics was in play early on. Primordial non-Gaussianity has to do with the interactions and the number of fields that were involved in inflation, says Ava Silverstein of Stanford University. A bounce would require gravitational effects beyond those of Einstein's theory, and cosmological observations can look for those. It's not something that would typically occur because gravity is attractive, so if you start contracting, you're going to collide, says Claudia Durham of Imperial College London. She and Gabbidatas have explored modifications to gravity that not only might let the universe bounce, but would illuminate the mysteries of dark energy. Modified gravity theories are a stepping stone to full quantum theory of gravity, and as such need to satisfy certain general principles. Those principles, along with observations, narrow the range of allowed modifications. That really constrains your allowed region of parameter space by combining observations and theory priors, she says. Once cosmologists open the door to modified gravity, all sorts of new phenomena come rushing in. And bounces are almost the least of it. Franz Pretorius of Princeton, an expert in computer analysis of Einsteinian gravity, has been simulating post-Einsteinian gravity. In one case, he and his students were tracking the formation of black holes when the modified gravity equations suddenly ceased to operate in time. They had changed their mathematical character from one that evolves to one that remains in a steady state. When something like this happens, we have no idea how to interpret it, he says. As impatient as theorists may be to settle what happened at the dawn of time, and whether time even had a dawn, Keating says his team plans to take it slow. They don't want to pass judgment before chasing down every possible source of error, not least their own potential confirmation bias, of which any scientist should be acutely aware. We spend so much time ruminating on what could go wrong, he says. We almost need a psychotherapist to help us with our self-doubt. This article is part of the 5 puzzles that continue to intrigue us section of the Foundation's 21st anniversary book. That comes from the Simons Foundation website. So here we see scientists struggle with the interplay between their self-awareness, their reputation, and so on, and their ability to understand things like primordial paradoxes in the early universe, what's going on. Their theories need testing, and when they go out to test it and they don't see what they have, They want to be cautious not to simply adjust their analysis. And that's not what they're doing here, to make sure that they haven't done something wrong. What they're doing is they're going back to the drawing board a bit to make sure, for instance, that all the parameters by which they're taking their measurements, all the settings, are correct. To update their theory while they're collecting data, to adjust the data in real time to theory would be wrong, but to adjust the theory to the data would be fine. Okay, so I promised you that we would be doing a second article, and the second article is a very interesting and quite related one. I do have to set it up a bit. So the Einsteinian theory of gravity, because it cannot reconcile itself with the strange observations of quantum mechanics, such as spooky action at a distance, superpositioning, particles that appear to be able to superposition themselves through solid matter, this continuum of matter, this probabilistic continuum of matter, it has a lot to do with the nature, the fundamental fabric of space and time. Many times when we think about space, we think about out there. We think about the universe. We think about galaxies, stars, black holes. We tend not to think about the fact that space is indeed the same thing as you go in the other direction. As we go larger and larger, we go from planets to solar systems to galaxies to galaxy clusters. As we get larger and larger in scale, we also have to remember that going in the opposite direction, going smaller and smaller in scale, that there are some strange features down there, as it were, within us, going on right now with our atoms and molecules, and going on for a very, very long time. Perhaps as long as, let's throw a number out there, 50,000 years after the beginning of the universe, maybe 380,000 years after the beginning, whatever it means to talk about the beginning of the universe. Now, there's a team at Penn State University, and they published an article alleviating the tension in the cosmic microwave background using Planck scale physics. Planck scale being the smallest possible scale that can be measured. To me, a rather arbitrary way to set a fundamental limit on scale. Remember when scientists talk about on the order of, they're meaning approximately so, plus or minus, an order of magnitude, or tens of orders of magnitude, or 1,000, 100 orders of magnitude. It really depends on what they're talking about, but on the scale of, relative to, as far as we know, over the next hill kind of thinking. And the Planck length, which I defined last time, is the amount of time that it takes a photon of light traveling at the speed of light to traverse a unit of distance over 1 Planck second. It's not very helpful. It's rather self-referential, because what is a Planck second? It's the amount of time it takes a photon to travel a Planck length. I guess the idea is that no one would be smart enough to come up with a way of measuring something smaller than a Planck length if they were looking using photons. However, I would tend to disagree. I think we can measure things much, much smaller than the Planck length if we simply take repeated measurements and adjust our observer by half a Planck length, for instance. If we jitter the location between the observer and the object we're trying to measure, and then through image convolution, we should be able to see what the average photon tells us. this type of imaging should be able to go much, much, much smaller than a Planck length. However, nevertheless, looking at an article in Daily Galaxy, The Daily Galaxy, at dailygalaxy.com, published in July, about the Pennsylvania State University's work, is a fascinating exploration. They're talking about quantum loop theory. And quantum loop theory came about originally, in part, as an alternative to general relativity, because general relativity was unable to explain some of, or anticipate, or reconcile itself with some of the issues of quantum mechanics. And loop quantum theory, or LQT, came out of a search for basically a general theory of everything, grand unification, just like string theory and other theories. They compete with each other to some extent. And we have people who support string theory. We have people who support loop quantum theory. I'm not in any position to be able to take a hard stand on any of it. I'm a passive observer of a fascinating period of time in science. So I'd like to share with you what the Penn State University group did, as is represented by this article. The title of the article is Primordial Paradox: Quantum Fluctuations in the Early Universe. In the end, the most improbable and hence the most puzzling aspect of space is its very existence. The simple fact that we live in an apparently smooth and regular three-dimensional world represents one of the greatest challenges to the developing quantum theory of gravity, wrote physicist Lee Smolin in 3 Roads to Quantum Gravity. If you look around at the world seeking mystery, you may reflect that one of the biggest mysteries is that we live in a world in which it is possible to look around and see as far as we like. The great triumph of the quantum theory of gravity may be that it will explain to us why this is so. 2 major mysteries about the large-scale structure of the universe may be explained by tiny quantum fluctuations in the early universe. The primordial fluctuations we are talking about occur at incredibly small Planck scale, said Brajesh Gupta, formerly a postdoctoral researcher at Penn State, currently at Texas Advanced Computing Center of the University of Texas. A Planck length is about 20 orders of magnitude smaller than the radius of a proton. But corrections to inflation at this unimaginably small scale simultaneously explain 2 of the anomalies in the largest scales of the universe in a cosmic tango of the very small and the very large. Quantum fluctuations can pre-exist, that is, precede physical law, according to Sten Odenwald, an astronomer at the NASA Goddard Space Flight Center. So, in the Big Bang, the establishment of, quote, law came after the event itself, but of course, even the concept of time and causality may not have been quite the same back then as they are now. The Penn State study, which appears online July 29th in the journal Physical Review Letters, also provides new predictions about the universe that future satellite missions could test. Tiny inhomogeneities of the cosmic microwave background. While a zoomed-out picture of the universe looks fairly uniform, reports Penn State, it does have a large-scale structure. For example, because galaxies and dark matter are not uniformly distributed throughout the universe, the origin of this structure has been traced back to the tiny inhomogeneities observed in the cosmic microwave background, radiation that was emitted when the universe was 380,000 years younger, that we can still see today. But if CMB, the cosmic microwave background, itself has three puzzling features that are considered anomalies because they are difficult to explain using known physics. Using known physics. While seeing one of these anomalies may not be that statistically remarkable, seeing two or more suggests that we live in an exceptional universe, says Dongshu Zhong, associate professor of astronomy and astrophysics at Penn State, and an author of the paper. A recent study in the journal Nature Astronomy proposed an explanation for one of these anomalies that raised so many additional questions. They flagged a possible crisis in cosmology. Using quantum loop cosmology, however, we have resolved two of these anomalies, naturally avoiding that potential crisis. Research over the last 3 decades has greatly improved our understanding of the early universe, including how the inhomogeneities in the cosmic microwave background were produced in the first place. These inhomogeneities are a result of inevitable quantum fluctuations in the early universe. During a highly accelerated phase of expansion at very early times, known as inflation, these primordial, minuscule fluctuations were stretched under gravity's influences and seeded the observed inhomogeneities in the cosmic microwave background. Loop quantum cosmology. To understand how primordial seeds arose, we need to look closer at the early universe, where Einstein's theory of general relativity breaks down, says Abe Ashtekar, Evan Pugh Professor of Physics, holder of the Eberly Family Chair in Physics, and director of the Penn State Institute for Gravitation and the Cosmos. The standard inflationary paradigm based on general relativity treats space-time as a smooth continuum. Consider a shirt that appears like a two-dimensional surface, but on closer inspection, you can see that it is woven by densely packed one-dimensional threads. In this way, the fabric of space-time is really woven by quantum threads. In accounting for these threads, loop quantum cosmology allows us to go beyond the continuum described by general relativity, where Einstein's physics breaks down, for example, beyond the Big Bang. The researchers' previous investigations into the early universe replaced the idea of a Big Bang singularity, where the universe emerged from nothing with the Big Bounce, where the current expanding universe emerged from a supercompressed mass that was created when the universe contracted in its preceding phase. They found that all of the large-scale structures of the universe accounted for by general relativity are equally explained by inflation after this big bounce using equations of loop quantum cosmology. In the new study, researchers determined that inflation under loop quantum cosmology also resolves two of the major anomalies that appear under general relativity. The researchers also produced new predictions about a fundamental cosmological parameter and primordial gravitational waves that could be tested during future satellite missions, including LightBird and the Cosmic Origins Explorer, which will continue to improve our understanding of the early universe. Okay, so let's try to unpack this a little bit. A little bit of research that I've done on loop quantum cosmology. It's very, very dense. And that's okay. Essentially, they're motivated to try to explain some tensions, cosmological tensions. In the early 1990s, there was an excess large-scale power. Some of the parameters of their models were wondering what some of the fundamental values that would fit those parameters. In the mid-1990s, the age crisis, were there systematic errors in our null hypothesis? Was there systematic errors in our understanding of star cluster ages? And there's been some update to physics since, and the cosmic acceleration implies that time zero is proportionate to 1 over the null hypothesis. And in the mid-2000s, there was questions about the cluster mass-to-light ratios So they're taking measurements in the universe, and things didn't really fit. They call these cosmologic tensions. To whatever extent I misinterpreted that, I apologize. However, the team is hard at work trying to reconcile these differences to the point where everything seems to fit, unlike Einstein's gravitational theory. So it's clear that something should be done. Absolutely clear that they should be asking these questions. They have questions such as extra dimensionality that are worth contemplating. Many of the alternative theories have problems of their own, alternatives to Einstein. As I've come to understand a little bit about this, is the problem of reconciliation, of course, of quantum mechanics and general relativity to create a fully consistent, coherent theory. The question is, what does that look like? String theory was one attempt. This idea of a fabric of space-time is a bit ironic because the early cosmologists proposed that there was an ether out there in the universe upon which things existed. Floating in an ether, we travel from point 1 in space to point 2 in space. You travel through an ether, and now it seems like there is some idea of a fabric, a physical fabric of space-time. In episode 2, we talked about this a little bit. There are some strange things that happen in the deepest parts of the universe, such as the spontaneous resolution, I would call it, of matter popping into existence. A resolution of what? Where does it come from? Simultaneously popping out of existence. Where does it go? Are these energy states, just like an electron can acquire an energy state? Are there thresholds with which matter itself, being a probabilistic entity, condenses into something with mass? I think that those are self-evident questions. I think the use of the mathematics that are in play in these different theories are attempts to try to answer that. The space-time that we live in, is it fundamentally continuous or is it discrete? Does itself come in packets? Is gravity, like matter, quantized? Is time quantized? This is the origin of the search for particles such as gravitons. And if it is quantized, when they're talking about particles, they're talking about discrete packets. We have to be careful not to accept any determination of a discrete rather than a continuous measurement, however, based on the degree of resolution of instruments that measure what we're measuring. So, other open questions include, would a consistent theory involve a force mediated by a hypothetical graviton that I just mentioned? And this brings into question the inability of my mind to reconcile inevitable consequences with a force. For all intents and purposes, we say acceleration is the same as gravity because a person experiencing acceleration would not be able to tell the difference. I don't like arguments by analogy. Something's missing. That's an inexact analogy. Object A relative to object B experiences gravity, even if they're both accelerating. they experience acceleration even if they're both accelerating, or they're not accelerating. If they're both accelerating at the exact same rate, it would appear as though there's no gravitational pull between the two objects. However, is that real? The gravitational pull is there the minute you take away the acceleration. I think if we're accelerating alongside of it, and we put ourselves alongside of it, it would be very difficult to measure the gravitational pull. But we can measure the expected gravitational pull, and we can witness the effects of gravitational pull even as our very own solar system is racing through space-time. Our planets don't just ignore the sun, even though they are all traveling through space-time, accelerating or decelerating at approximately the same rate. So, again, if there's a consistent theory to be had, would it involve a force mediated by a hypothetical graviton or a product of a discrete structure space-time itself? Are those two things one and the same? Is a graviton not a product of discrete structure space-time itself, if a graviton exists? I think they've discovered a graviton. So, in loop quantum gravity, this is apparently an open question. Are there deviations from the predictions of general relativity at very small or very large scales, or in other extreme circumstances that flow from a quantum gravity theory? So, as you put together any model that is meant to explain anything, any model by definition will be incomplete. A model is a toy. A theory is a model. A theory, therefore, is a toy. And lately, I've been toying with the idea that perhaps the very way that we go about modeling is limiting our understanding of the universe, and limiting, very much so, our understanding of ourselves. Most of the time when we do our modeling, we focus on objects and the relations among them. I'm going to speak briefly in very general terms about the problem of relational representation and the limits of knowledge. This is just some meanderings. Everything I say over the next few moments is applicable to almost any area of inquiry. So-called hard sciences, so-called soft sciences, quantum physics, biology, sociology, psychiatry, systems biology. When we create a model to study relationships, the canonical way that the human mind works of studying relationships is to study the objects, a set of objects, think of them as a vector of objects, and the relationships among them. Now, you can think of those relationships also as a vector of edges. And if we use something called graph theory, we can actually map out in a diagram. There's many, many different kinds of graph theories, one of which would be like Sewell-Wright's path diagrams, for instance, that can be used in functional analysis. And the value of these graphs, of mapping out, just to make it concrete for the listener, if you think about your immediate family, all of the members of your family have relations. Those specific relations write everybody in your family, or your immediate family, one step removed, whatever, on a large sheet of paper, and then start drawing diagrams. So after you draw each circle for each person, you draw arrow diagrams. You draw paths from one to the other, and then you write sister, brother, mother, cousin, so on. Those are relational diagrams. And the value of the relational diagrams in science is that they help us make explicit some of the things that we don't usually see. Sewell-Wright, for instance, he was studying hamsters, And the inheritance patterns in hamsters and guinea pigs, and you have a male hamster, it's called a sire, and you have a female hamster, it's called a dam. And in the mating of hamsters and guinea pigs with different coloration patterns, he could observe the inheritance of these features, these characteristics, or these phenotypes of the animals in the offspring. So even in what I'm saying, you have the sire, you have the dam, they have a relation through mating. They also have other relations in terms of inbreeding, how closely related they are, for instance. But the offspring have well-defined canonical relationships between, the paternal parent and the maternal parent, the father and the mother, the sire and the dam. But what Sewell Wright did that was so useful is he laid them all out on paper, and he would draw the relationships. If you're studying phenotypes, these characteristics, there's the genetic influence. So he mapped out the genetic influence. He mapped out the information flow from the sire through the sperm and the dam through the ova, the eggs, and interrelationships among them, of course, with mating. And the heritability of the trait is made explicit. Heritability being a relationship, it's not an object. So in a path diagram, you can make these objects really explicit. You can make the relationships really explicit. He also included chance, just probabilistic chance, right, where the clock approximates reality. Now, part of my bugbear on modeling, and this is not a critique of how we do it, this is a mental exercise in how we can do it better, is that we were really bad at estimating dimensionality of what we're studying. Humans are awful at understanding the true dimensionality of what we're studying. This is for a large number of reasons, all of them legitimate, but collectively they make our models terribly oversimplified. Let's go through them. The first factor that causes us to not be able to understand dimensionality very, very well is tradition. We tend to build our existing models on pre-existing models when hardly anyone starts from scratch. That makes us, understandable to our colleagues, but it also makes us extremely prone to something called error propagation. So if the previous generation's models have an error, a fundamental error, a profound error, we inherit that error. We don't even look at it. We might not even see it. I mean, who's going to question Einstein, for instance? I think now enough time has passed and enough data have been collected that say, we need to question Einstein in some serious ways. And it's okay and normative to talk that way, but it took a long time before it was generally accepted. Of course, another factor that causes us to miss out on the degree of granularity when we do our models is ignorance. There just might be missing parameters. Ignorance is simply the lack of knowledge. And it should not be confused with stupidity, and it should not be confused with a mental attitude. It simply is a mental state of being where you simply don't know something. One form of ignorance is just missing parameters. You don't know that you should measure something. You don't know you should consider something. And those are two different things. If you don't know something exists, you can't measure it. You might predict it as they do in quantum physics, and that's one of the beautiful things about theoretical physics. In this quest for understanding as part of fundamental physics, it makes predictions which then empirical science, empirical physics can then test out. But if you don't even know that something exists or should exist, your model is going to be misspecified due to ignorance. Another form of ignorance is you're just missing an understanding of relationships among objects. And of course, those can compound. If you don't know something exists, you can't postulate a relationship between anything and it. There's something uniquely characteristic to the history of our science, and perhaps to our species, in that we have an annoying and unrealistic preference for features of models, like simplicity and beauty and elegance. Why is it annoying? It's annoying because, well, we tend to cancel things out mathematically at every opportunity if they're on the other side of that dividing line. We tend to take our piece of chalk and cancel out E or T or S or M or whatever variable seems to cancel out, as if that canceling out helps us. I mean, if you have a more expanded form of an equation, that expanded form of the equation works just as well in its operations as the simplified form. There's also this kind of haughtiness to the thought that perhaps people who don't recognize and can't cancel things or refuse to or unable to cancel things out might just not quite be right. They might not be as intelligent as others and things like that. And once you put that aside, then and you realize that two equations or two computer simulations that work equally well, one that has 5 terms versus one that has, stated explicitly, and one that has 4 terms stated due to canceling. They work perfectly well. The argument, I think, could be made that through provenance of the original relationships and how the equations are structured might stimulate a better understanding of the ignorance of the relationship information we were just talking about. So this tendency to cancel things out reduces the dimensionality of our models by definition, in that we might not think to postulate new relationships among the parameters that we know or we think we should include. And I'm going to give you an example of that in a moment, but the last kind of tendency that we have is to use models. Using models are models. If someone were to create a perfectly working model of the universe, it would be the universe. If someone were to create a perfectly working airplane model, we could fill it up with fuel, we could load it up with passengers, put some pilot and co-pilot in there, get approval, and we could fly this model across the country. In other words, a perfect model is the object itself. And so the dimensionality, why I'm stuck on this for a moment here, is that in physics, there's a fundamental assumption that's been made from the beginning, very beginning, and we all are amazed at this uncanny fit between the mathematics of physics and reality until it breaks down at the edges. In physics, we tend to assume that time past, time present, and time future are all fundamentally identical. They cancel out in the derivation of the theory of general relativity. And this goes against all empirical evidence. All empirical evidence, including our own personal experience, tells us that time past is different from time present that's about to happen, that's happening right now, in time future that is not yet to happen. In fact, we say intuitively in the English language that time past does not exist. It's gone. It's literally gone. We say intuitively that time present is now. And we say intuitively that time future is to be. It has yet to become. Does not yet exist. So our direct empirical observation tells us that there is something fundamentally different, for an observer anyway, if you want to stay in relativity, of time past, time present, and time future. The fact that time cancels out of all the special and general relativity equations and all subsequent models that derive from that has been something that has bothered me for some time. We humans tend to underestimate the dimensionality of the universe, and the mathematical derivations are more complex, they're less elegant, they may even be considered ugly. They may not be as beautiful or elegant, but I think it's worth contemplating. What if there is some difference in some aspect of time past and time present and time future? In my explorations in this, the explanation is, well, they cancel out, therefore they are the same. Gee, isn't it marvelous that time everywhere at all times is the same, is a complete 100% tautology. It's a circular argument. The fact that it cancels out of Einstein's equations is due to an assumption that they are the same. The fact that time has nothing to do with general relativity. There's no time in the equations is a result of an assumption. It is not proof of itself. We'll be visiting this point time and time again in the future, I'm sure. But back to my original thought about these relational representations and the limits of knowledge. It's not apparent that time past, time present, time future are different if you simply represent them on the page as time. They're something, it's t sub 0, t sub 1, t sub 1 plus n, where n is the number of steps into the future you may be going. You can also do t sub I minus x. You can represent these things however you want to specify any particular point in time relative to an observer. But let's talk about the relationships between the observer and the universe. A short list of the relationship between the observer and the universe includes that the observer can observe the universe. It also includes that the observer is part of the universe. It includes that the universe can observe the observer. Other people can observe us observing the universe. Another relationship is that the observer can change the universe. And further, if you're a human being anyway, the observer can imagine the universe. This means that the observer can imagine the observer imagining the universe. That's metacognition. If I think about myself thinking about the universe, I'm thinking about it. And I'm sure fundamental physicists driving to work wondering what they're going to do. I think today I will work on quantum loop cosmology. That's the universe thinking about themselves, itself thinking about the universe. If you think about that, that's kind of cool. Now, in terms of causality, it gets a little complicated because, we have the fatalists who think that the universe is headed down a particular path as a necessary set of consequences. And yet here we are. We're in a strange universe that apparently needs further explanation, but yet here we are. And so we have to wonder, is the universe a set of special conditions in which the observer might be possible? Are there other universes that could have arose in which we ourselves as such are not possible? So it's proper to speculate that the universe may be a set of special conditions within which the observer may be possible but not inevitable. Still, the universe is, as we know it, a set of necessary and sufficient conditions for the observer to exist. And this is a fancy way of saying that the universe, in one form of causality, causes the observer to exist. The failure to prevent the observer from existing, having all the necessary conditions, allowing it. This is why my mind tends to focus on inevitable consequences as opposed to forces. Inevitable consequences as opposed to causes. And my mind tends to focus on emergences as opposed to consequences anyway. So the final relationship we should contemplate is that some actions on the part of the observer can cause the resolution of a state of part of the universe. And this, of course, refers to the collapse of the state function of subatomic particles that are in superposition. You can't tell where they are because they are, for all intents and purposes, in multiple places until you measure one, and then you know where it is in 4 dimensions of space and time. So we can have some fun with this kind of thinking about these relational statements, relational representation, such as I can say something like the universe is a set of necessary and sufficient conditions by which the observer can exist. And if there is an observer, the observer can be observed by other parts of the universe while the observer is imagining the observer measuring the universe. That is not nonsense. That's not gibberish. That is not an infinite regression. These are loops. And it's fascinating that quantum loop theory exists. The universe feeds back on itself, for sure. Now, if you represent the observer, we're focusing on the relational representation between the observer and the universe. If I say the observer and the universe, it's a difficult thing to understand because from a pure relational standpoint, the observer is part of the universe. So how can I separate the observer from the universe? And the minute that you recognize that the individual observer is part of the universe, you recognize that at any given time when it's observing part of the universe, if it's multisensorial like we are, we have multiple sensory inputs, it's aware of, or to less or greater degree, of many different parts of the universe at the same time, other than the one that it's measuring, and also it, of course, can be aware of itself making those measurements. Fascinating thing is that the observer can observe relationships, or they can deduce relationships, which is the same thing as observing them if they have them correct. So the question that I'd like to pose is, why do we represent relational relationships secondary to objects? Earlier I said you can write your family out on a piece of paper and you can state all the relationships among your family or friend network. Why do we represent relations in that network secondary to objects? We use the arrows to represent relationships. This is a natural tendency, and this is how a lot of mathematical models map to the same kind of thinking. That, we don't understand general relativity, how it breaks down at small scales, because we lose scale. At large scale, we lose the ability to see. At high speeds, we lose the ability to measure, perhaps. An entirely different representation would define the relationships at the points and the objects at the edges. Imagine the relationships being the primary thing that you write out. So you write out the word brother, sister, mother, cousin, so on, and then represent the relationships among the objects or your family members. This makes some things happen in the statements of relationships that does not happen in the canonical way with which we represent them in our modeling. In canonical relationships, we tend to focus on the objects as entities. Imagine a vector of objects and the relationships among them. And we can do this generically in graph theory using a collection of edges that exist or they do not exist, and we can color those edges based on the nature of those relationships. Imagine for a moment the statement, consider for a moment the statement, the passenger travels among the stars in a spaceship. The passenger is an object, stars are an object, the spaceship is an object. The relations are travels and what? There are other relations that are not made clear by that English statement. The perfectly clear English statement, the passenger travels among stars in a spaceship, implies that there's a relation. What is the relationship between the passenger and the spaceship? It's not made explicit. The relationship between the passenger and the spaceship is that the spaceship carries the passenger. Another relationship is that the passenger may operate the spaceship. The passenger travels among the stars in a spaceship also implies that the passenger enters and stays in the spaceship. And nowhere in the sentence, the passenger travels among the stars in a spaceship, did I say that the passenger is entering the spaceship. Perhaps the passenger is born in the spaceship. That's why I could be incorrect about that relationship. But nevertheless, at some point in time, something that brought about a passenger being in a relationship, some relationship occurred, existed. And so if I just graph this out very simply with the passenger, stars, and spaceship as objects and the stated relations, and I leave out that the passenger entered the relationship, the passenger stays in a relationship, you see all models are simplifications, and a sentence is a model of reality. But now if we invert that process and we make the relations the objects, and the circles on the page are travels, carries, enters, stays in, and the edges, if we relate the relationships through the objects, something remarkable happens. First of all, it looks very funny. It takes a while for the human brain to accept it. But on the page, if we do a relation-object analysis, we have observes as one spot, carries as another, enters, stays in, and travels. Why do we have observes as one spot? Well, the passenger is observing the universe as it goes through it. It's observing the stars. It's observing the spaceship. We didn't even include that in the last one. See how dangerous it is to use simple object first relation analysis. Object relation analysis hides many of the relations. Relation object analysis forces us to make the relations more explicit. So let's slow down a minute and think about this. We have a passenger who's in a spaceship and traveling through stars. Imagine, if you will, on a sheet of paper, arrows labeled passenger, spaceship, and stars. That is, these relations relate to each other through the objects. This is an inversion of the normal way of thinking, but it forces so much more transparency. So now we know that the spaceship and the passenger are related through travels, stays in, and enters. And we know that passenger and stars are related through observes. Passenger and spaceship also has an observes. And stars and spaceship are related because the spaceship is passenger, so that's a secondary relation. There's another relation, of course, that the spaceship was made probably of stuff from one of the stars, ultimately. So you see, it's very natural then and intuitive to expand the relations that are being considered. And this relation object analysis is something that might help in the area of quantum physics. It might help in the modeling of sociological phenomenon. It might help in psychology. It might help in systems biology. In part because it groups the relations. So the relations observes, enters, stays in, and travels they all share something in common that are different from carries, let's say. Okay. So there are differences. The passenger doesn't carry the spaceship. There's directionality in these diagrams that I imagine that might be helpful. So the conclusions that I come to through this thinking are that object relation representation is a lossy transform. We lose information simply by not forcing ourselves to make explicit all of the relations through objects. Implied juxtapositions of objects and implied juxtapositions of relations are not made evident in object relation representation. And the assumptions about their nature, if we come to an object relation representation as opposed to relation object representation, the assumption about the nature of the objects and their relations limits model specification. It's the same thing as saying it's a lossy transform, but it's worth stating that. And so I hope that relation object analysis proves useful to someone. I'm sure there's some very smart people out there that could make a program that could recode human English languages, Spanish, French, all kinds of languages, German. And this is not about grammatical structure. This is a fundamentally different representation that leads to different ways of asking questions, because you might not think to ask questions, and I call it shaking the tree at the root. If you shake the tree at the root, grab the trunk near the root and shake it, the tree of knowledge, you have a much better chance of learning something than adding something to the tips of the tree. So that was fun. I'm going to close with an observation that the observer imagining the universe is an example of the universe imagining itself imagining. I'm Dr. James Lyons-Weiler. It's been a great deal of fun and an honor to spend this time with you. As always, through due diligence, I'd like to send you over to patreon.com at WWDNYK if you'd like to see more episodes like this. This is episode number 3. We have some guests that are interested in coming into these discussions as we progress. We have another 150 or 60 so articles to get through, I'm very happy to say. It's a fascinating time to be a scientist, and I hope that this took you away from your troubles for part of the day.